morning, fellow mathematicians, welcome back to another video. What we are going to derive today is the basis for a lot of analytic number theory, so it's pretty fucking important. It's going to be the basis for the very next video. Today we are going to derive the series expansion by Mittag-Leffler of the cotangent. It's pretty damn important, and yeah, we are going to do it using Daddy Fourier transform. Right here, Fourier series, not transform, I'm terribly sorry. And well, we are going to take a look at exactly the cosine of t times x on the interval from negative pi to pi, meaning some stuff is going to cancel out right here, this 1 over pi and those arguments of the sine and cosine. So that's p good. And also I want to place a little restriction on t. We don't want t to be element of the integers. Otherwise it would cause problems. You are going to see this in a few minutes. So we want t to be element of the real numbers without our boys, our main boy, the main spider, the integers. So we are going to go ahead and get started. I want you guys to remember what a naught over 2 is. A naught over 2 is nothing but 1 over 2 times L, but L in this case is nothing but pi. So 1 over 2 times pi. An integral from negative L to L, so negative pi to pi, of, okay, this is just our function integrated with respect to x. So meaning this is going to give us the cosine of t times x integrated with respect to x. Simple Fourier coefficients we are going to derive them today. I want you guys to notice that the cosine is an even function, meaning over the symmetric integral is the same as saying we have 2 times the integral from 0 to pi. I made a proof on that, take a look at that. Meaning the 2 and the 2 is going to cancel out then, so it's just going to be 1 over pi in the end. So this makes things a little bit easier. Also integrating this is really quite easy. It's going to give us 1 over t times the sine of t times x. So this is 1 over t times pi times the sine of t times x. Evaluated from 0 to pi. Meaning if you plug 0 into here, it's going to vanish. Sine of 0 is 0. If you plug pi into here, well, this is the sine of t times pi. So you see, not element of the integers, coolio, so not 0 or negative 1 or whatsoever. Meaning this is going to evaluate to the sine of pi times t over t times pi, or sine of t times pi. Then I want you guys to take a look at Burger King right here, BK. This is going to be 1 over pi times the integral from negative pi to pi of the sine times the cosine of some sort. Sine times the cosine is going to be an odd function overall. Meaning if we integrate an odd function over a symmetric integral, it's going to vanish. Meaning our Burger Kings are nothing but 0, so this part is going to vanish. Coolio, we got rid of that. Now for our AKs right here, AK 47. AK is nothing but 1 over L, so 1 over pi, times an integral from negative pi to pi. It's going to be an even function in here, check it out for yourself. So once again we can use this symmetry argument to turn this into 2 times the integral from 0 to pi of cosine t times x times the cosine of k times x, integrated with respect to x. This is integrable in many different ways. I'm just going to make use of integration by parts. That's the easiest right here in my opinion. You can also make use of real part stuff of the complex exponential function. Never mind, we are not going to give a shit about that. I'm going to call this thing right here I for now, and we are going to take a look at that. So our I is nothing but we need something to differentiate and something to integrate. Why not differentiate our boy cosine t times x? And we are going to integrate our main spider cosine k times x. Plus minus 2 iterations, we have to do 2 iterations. Actually, differentiating this leaves us with negative t times the sine of t times x. Differentiating this once more is nothing but negative t squared cosine t times x. Alright, if we integrate the cosine, it's going to give us 1 over k times the cosine k times x. Integrating this another time, not the cosine, the sine, I'm terribly sorry. Integrating this a second time is going to give us negative 1 over k squared cosine of k times x. And you see integration by parts works wonders here because we are going to actually recover our integral I in the process. Meaning overall we are going to multiply this and that together. But before we actually do that, I want you guys to consider this multiplication right here evaluated at the upper and lower bounds, 0 and pi. If we plug 0 into our sine, it's going to be the sine of 0. This part is going to vanish. Also, if we plug pi into here, k is element of the integers, meaning every time we have 0, pi, 2 pi, 3 pi, negative pi, it's going to be 0. So overall, this diagonal multiplication is going to vanish on the upper and lower bounds. Now, maybe you can hear it, my nose is a bit full of hay flu. It's so annoying, this time of the year starting again. Also my skin is just killing me, it's so sensible in less time. Also we are going to multiply this together. This negative sign and this negative sign is going to cancel out, but we are going to have this negative sign right here. So overall this is negative. So this is negative t over k squared, and then we are going to have the sine t times x times the cosine of k times x. Then, multiplying this together leaves us with positive t squared over k squared times an integral of this stuff. But this in itself is our I once again. So this is going to give us plus t squared over k squared times our I that we originally have. I've used this method so many times before, so I'm terribly sorry if I'm rushing through it, but it's so trivial, I don't want to hang myself up or something like this. Now we can subtract this on both sides. We are going to get that 1 minus t squared over k squared. Oh, and this from 0 to pi, I'm terribly sorry. Times I is nothing but, okay, we can advance this fraction by k squared over k squared, leaving us with k squared minus t squared over k squared times I being nothing but. If we plug 0 into here, this is going to vanish once again, so that works wonders. Cosine of k times pi, I've talked about this a lot of times before, is going to give us negative 1 to the kth power. And this is just sine of, well, t times pi once again. So this is negative t over k squared. And then we are going to have the sine of t times pi, negative 1 to the kth power. Coolio. You see, k squared and k squared is a common factor right here. We don't want it to be equal to 0. This just stems from the fact that our Fourier series starts at 1, so that's not 0. We can cancel it out on both sides. Dividing both sides by this k squared minus t squared term is going to leave us with, if this is not equal to 0, I being nothing but, okay, this is negative t over k squared minus t squared sine of t times pi, negative 1 to the kth power. Okay, so you see this is our integral I, and don't forget your factor of 2 over pi right here. We are going to multiply it by that, and then we can plug all this stuff into our Fourier series right here and see what we actually get. Maybe you guys have already also seen why there's another reason for us not wanting to have t being element of the integers, just because of this right here. If t could be element of the integers, then we could possibly divide by 0, but this isn't the case. Okay? K squared is element of the integers, and if you can subtract an integer from it, well, it doesn't work out. It's never ever going to be equal to 0. Okay, let us move on. I've plugged everything in, and as most of the times, we would like to evaluate this expansion right here at some x value. And you see, the cool thing is, why not evaluate this at pi, for example, okay? We're doing this on a closed interval pi or an open interval. Why not choose a closed interval for it? It's valid on here. If I plug pi into here, we are going to get cosine of x, cosine of pi times k. It's negative 1 to the kth power, meaning we are going to get negative 1 to the 2k power. Negative 1 to some even power is always going to be 1. We are going to get rid of this thing right here, and well, let's see what we then get. So the cosine of t times pi is nothing but the sine of pi times t over pi times t, t times pi, whatever, minus 1 over pi, and then we are going to get a sum running from k equals to 1 to infinity of 2 times t over k squared minus t squared sine of t times pi. And you see, one other reason why we didn't want t to be element of the integers is because sine of t times pi is then never ever going to be equal to 0. Meaning we can divide both sides safely by sine of t times pi to get cosine of some argument over sine of some argument is going to give us the cotangent of the said argument. So that's equivalent to saying we're going to have the cosine of t times pi over the sine of t times pi. Well, this thing right here is exactly the cotangent of t times pi. And then, what else do we have? We are going to get rid of this thing right here, so we are going to have 1 over pi times t minus. Why not bring some stuff to the inside, for example, just to make it look a little bit better, and some stuff to the outside. So let's distribute negative sign into here, turning around this order, and let's bring the 2 times t to the outside, so positive 2 times t over pi, sum running from 1 to infinity of, well, we got rid of the sign right here, so this is nothing but 1 over t squared minus k squared. We are basically done. So this right here is one expression which is equal to our boy, the Mittag-Leffler series expansion for the cotangent. One thing I would like to do, I would bring it into the proper form that you are going to find in most textbooks, probably. We are going to let t times pi be equal to something else, for example z, so making it valid for example complex characters right here. So by saying that t times pi is nothing but z, we are going to get the cotangent of z being equal to 1 over z in this case, plus, what is t exactly? Well, t is nothing but z over pi under the condition that pi is not equal to 0. It's not, I made a proof on pi being equal to 4. Take a look at that. So pi is definitely not equal to 0. Okay, then we are going to get 2 over 2 times z over pi squared times the sum running from k equals to 1 to infinity of 1 over, okay, like I said, t is nothing z over pi, so z squared over pi squared minus k squared. One thing we can do, we can factor out the 1 over pi squared. Okay, if we factor that out, we are going to get the pi squared right here and the 1 over pi squared to the outside, but it's 1 over pi squared, so imagine this right here. Okay, exactly this, giving us pi squared. This pi squared and this 1 over pi squared is going to cancel out in the process. Okay, just take a piece of paper, try it out for yourself as always, leaving us with a final expression for the cotangent of z being nothing but 1 over z plus 2 times z, sum running from k equals to 1 to infinity of 1 over z squared minus k squared times pi squared. And this is basically it. For reasons that will become apparent in the next video, it comes in handy to factor out the negative 1 once again that we have distributed into here initially. Okay, so this negative went into here, but never mind. This is our final expression for the series expansion of the cotangent brought to you by Mittag and Leffler. It's pretty damn important, and if you did enjoy this video, please like and subscribe and recommend the channel if you like, if you want to support the channel a bit more. Buy those t-shirts I created. I'm not wearing one of those right now. Actually, I'm wearing nothing under this right here. Whew, that's hot. Daddy being really hot right here. Some nip action. Never mind. You can also support the channel on Patreon. Take a look at my website, blah blah blah, second channel. And up until the next video, have a flammable day. Love you guys, appreciate ya. Ciao. Top 10 best anime battles.